Hello and welcome back to Survey of Biology. Today we're going to continue our talk of genetics and Unit 10. This is going to be Section 3. And here we're going to talk about probability and Punnett squares and how that applies to genetics. So if you look at the big picture, probability is just the chance that an event or events is going to happen based on the number of possible outcomes that are present. So like say if you flip a coin, what are the chances of getting a head? Well, the chance of getting a head would be 1. The number of possible outcomes is head or tail, so that would be 2. So the probability of getting a head is just 1 over 2. Okay? What if we had, instead of a coin, what if we had a die? So if we're going to roll a die, a 6-sided die, what are the chances of rolling a 3? Well, a 3 would be one event. There's 6 sides, so the probability of rolling a 3 would be 1/6. So we're going to apply that to our genes, the genes that we inherit from mom or dad, and how that applies to genetics. So a few rules to go over real quick. The rules of probability are based on a scale that goes from 0 to 1, with 1 being the event is certain to happen, 0 being the event is certain not to happen. So if we look at a coin toss again, if we flip a coin, what are the chances that we're going to get a head? Well, it's 1 out of 2, so it's 1/2. What are the chances that we're going to get a tail? It's also 1/2. Well, if we flip a coin, something's going to happen. It's going to be a head or a tail. So 1/2 plus 1/2 gives us 1. So something, the event is certain to happen, and it's a 50-50 whether it's a head or a tail. So if you look on this continuum here, if we start over on the far left, where there's the 0, so something here is impossible to happen. And as we move towards the right, we move from something being impossible to something being unlikely. So if we roll a die, the chance of getting a 1 is a 1 in 6 chance, which is relatively unlikely. As we continue to move to the right, we get to the middle where we have an even chance. So if we flip a coin, there's a 50-50 or a 0.5 chance that we'll get a head or a tail. We continue to move to the right, things become more likely. So the chance of drawing a blue ball out of this bag right here would be a 4 in 5 or an 80% chance. And then finally we get to the far right. Here's something that's certain to happen. It's got a 100% chance of happening. So the first rule we're going to look at is something called the rule of multiplication. And what this says is that the chance that 2 independent events will occur simultaneously is equal to the product of the individual probabilities. So if I have 2 coins and I flip them, I want to know what are the chances of getting a head and a head, so 2 heads. Well, the chance of getting a head on the first flip is 1/2. The chance of getting a head on the second flip is also 1/2. So 1/2 times 1/2 gives us a 1/4 or quarter chance that we'll get 2 heads if we flip a coin twice. The key thing to remember is when we're going to apply the rule of multiplication is when we see or when we can use the word and. So an example would be if you have a family that is going to have 2 children, what are the chances that they will have a boy and a second boy? So both children will be boys. Well, what are the probability that we're going to have a boy? Just like flipping a coin, the chance of having a boy is 1/2 times 1/2. So that family has a 1 in 4 or 25% chance of having 2 boys if they have 2 children. The second rule is called the rule of addition. We're not going to use this one as much, it's a little bit trickier, but this is the probability of an event that can occur 2 or more different ways is the sum of the separate probabilities. So now we're going to look at flipping coins again, but now what we want to look at is what's the chance of getting a head and a tail, okay? Well, there's 2 ways of getting it. We can flip the coin and get a head and then a tail, or we could flip a tail and then a head. In terms of probability, it doesn't really matter which way we go, but we've got a 1/2 chance of a head, a 1/2 chance of a tail. So that's 1/4. Or we could do the tail first, that's a 1/2, the head second, that's 1/2, that's also a 1/4. And in this case, because it's the rule of addition, 2 things that it's either or, we're going to add those, so 1/4 plus 1/4 gives us 1/2. There's a 1/2 chance. Now if we look at that over here and we divide up heads and tails, we can see there is 1 box, so there's a 1 in 4 chance that we'll get 2 heads. there is one box, a 1 in 4 chance that we'll get 2 tails, but there's 2 boxes, so a 50% chance that we'll get a head and a tail as long as the order doesn't matter. So the big thing to remember here is the rule of multiplication is when we see the word and. The rule of addition is when we see the word or. It's either this event or that event. So let's kind of take a look and see how that works out. So here's a jar of marbles. And in this jar, if I said, if we kind of blocked it out and said, I want you to reach in and tell me what are the odds that you're going to pick a red marble. So the red marble, there are 3 of them out of a total of 10. So that would be a 30% chance of choosing a red marble. Okay. Now, how about a green marble? It's a very light green, but hopefully you can see it. There's 2 out of 10, or a 20% chance of drawing a green marble. And finally, what are the odds that if you reach in, you're going to pick a blue marble? Well, if we count up the blues, there should be 5 out of 10. So there is a 50% chance that you'll get a blue marble. And what are the chances that you'll get a marble? If those, they should, all add up to 100%. So there's the odds of choosing each of the individual colors. Now let's look at a couple of scenarios. So the first one is, what are the odds of selecting a red marble? And that's what we did in the previous one. So that comes out to be 3 out of 10. And that should be relatively straightforward for you to see. But now, what are the chances that we can select 2 green marbles? Well, here's an and. I want to do a green and another green. Well, the probability for the first one would be 20%, 2 out of 10. And now, since there's only 9 marbles left, this probability of the second one would be 1 out of 9. So 2/10 times 1/9, we're going to use the rule of multiplication, gives us a 2.2%. So not a great chance of picking 2 greens in a row. Now, let's look at another scenario. What's the probability of selecting 1 blue, replacing it in a jar, and then selecting 1 red? Well, what are the chances of drawing a blue? Well, the chance of drawing a blue is 5 out of 10, so that's 50%. We then put it back in the jar, and then what's the chance of also selecting a red? Well, the red would be 3 out of 10, so this would be 5/10 times 3/10, and that gives us a 15% chance. So here again is the rule of multiplication. And finally, let's look at a scenario where we're going to use the rule of addition. Okay, so now what's the probability of selecting a blue or a green? Well, the chance of selecting a blue is 5 out of 10. The chance of selecting a green is 2 out of 10. And since it's either or, we're going to use the rule of addition. We add 5/10 plus 2/10, and there would be a 70% chance of reaching in and getting a blue or a green on the first shot. So now that we know a little bit about probability, let's go and apply it to genetics and talk about some Punnett squares. So what we're going to look at real quick is something called a monohybrid cross. So this is looking at one trait. In this case, it's going to be a gene for yellow peas. So big Y is yellow, little y is the recessive, which would be a green color. And if we see a couple terms, here is heterozygous dominant, big Y, and this individual here is let's go back. This is homozygous. I'll write that out so I can remember. Dominant. And this one is homozygous recessive. So a few terms to remember. And if we take the homozygous dominant individual, the only gamete that they can produce is going to be big Y. If we take the homozygous recessive, the only gamete that they can produce is little y, and we set up a Punnett square. And in this case, it's going to be a 2 by 2, because each parent is going to produce 2 gametes. So we'll have 4 offspring. And in this case, all will be heterozygous. So all of them will have the same genotype, big Y, little y. So again, genotype and phenotype, and the phenotype of all of these, since they're dominant, will be yellow. So there's a very simple monohybrid cross. Okay, so here now is a cross between a pea plant that is homozygous for yellow, okay, and a pea plant that's homozygous for green. This is what we just looked at. So here is the same thing. So we have the gametes here, little y, same thing here, big Y, and in this case, all four are going to be heterozygous yellow. They're going to express the dominant trait, and that's a 2x2 Punnett square. Now let's expand. So now let's look at two individuals that are going to be heterozygous. So they're going to have either a big Y or a little y. And the same one over here, big Y or a little y. So if we fill in, if we go over and down, this individual is big Y, which makes him yellow phenotype. Go down and over, and this individual is little y, which makes him homozygous recessive, and it's going to be green. And the two in the middle, big Y, little y, big Y, little y, we have two that are going to be, two that are going to be heterozygotes. So what we get here is we get different ratios that we need to be familiar with. So this is for a heterozygous cross. And if you remember the phenotype, which is the physical type, the physical appearance, is going to be 3 to 1. We're going to have 3 dominant yellow, 1 recessive green. That's what they're going to look like. Now the genotype is going to be, as we can see it over here, 1 to 2 to 1. We'll have 1 that's going to be homozygous dominant. We'll have 2 that are heterozygous, and we'll have 1 that's homozygous recessive. So we've got to remember these genotypes, 1 to 2 to 1, and phenotypes 3 to 1 when we look at this. So here's our monohybrid cross again, and you can see the same thing. And the big thing that I want to highlight here is, again, looking at these ratios. So the genotype ratio, if it is a heterozygous cross, so both parents have to be big Y, little y, we're going to get a 1 to 2 to 1 genotype ratio, and we'll get a 3 to 1 phenotype ratio. So let's look at a couple examples real quick here. So here's an example where we have a heterozygous parent for the tall gene. So the big T makes it tall, the little t would be a dwarf pea plant, and this is homozygous. So let's go and fill in. If we fill across and down, we have big T, little t, big T, little t, little t, little t, little t, little t. So our genotype ratio, the type of genes they have, would be a 1 to 1, because half of them would be big T, little t, and half of them are going to be little t, little t. Now what about our phenotype ratio? Our phenotype ratio in this case is also going to be a 1 to 1, and it's going to be half of them will be tall, half of them will be short. So 1 to 1 ratio, 2 to 2 reduces to 1 to 1. So if we go and we look again here, let's do the same thing here. So we've got big B, little b, big B, little b, little b, little b, little b, little b. So again, our genotype is a 1 to 1. Whoa, hang on there. Our phenotype is also a 1 to 1. Sorry about the scribble there. And in this case, it's brown eyes, the dominant, to blue eyes, the recessive. And so to kind of wrap it up, we can look at here is a Punnett square of daddy genes that love chocolate, mommy genes that love vegetables, and we can see the love of vegetables is recessive. So how many of the offspring of this mother and father are going to have a love of vegetables? Well, if love of chocolate is dominant, 0%.